A black hole's grip on reality is absolute. But what if the cosmos has a secret opposite, a place where gravity runs backwards and existence violently erupts? We are hunting for the universe's most elusive theoretical objects, distant white holes. By the end of this journey, you will hold 25 mind-bending facts about these cosmic enigmas, pieces of a puzzle that could redefine physics itself. We will travel to the edge of time, to the aftermath of the Big Bang, and confront mysteries that challenge cause and effect. What do you believe lies at the absolute frontier of our understanding? The concept is rooted in the pure, elegant mathematics of relativity. Einstein's field equations, the very rules that govern gravity, are symmetrical with respect to time. Run the clock forward, and a massive star collapses into a singularity, creating a black hole, a point of no return. But run the clock backward on that exact same solution, and the mathematics spits out something astonishing, a region where all that collapsed matter and energy violently explodes outward from a central point. This is the white hole, a cosmic fountain of creation that cannot be entered, only exited. It is a place where gravity, the force that pulls everything together, seems to have reversed its role entirely. Picture watching a film of a black hole devouring a cloud of gas and then hitting rewind. You would see the gas erupting from the singularity, shooting out into space at incredible speeds, defying the pull that once consumed it. That reversed film is the simplest way to visualize a white hole in action. It is not merely a different object, it is the same object seen from the opposite direction of time, a mathematical mirror image that challenges our most basic intuition about how the universe flows. This mathematical mirror leads us directly to our second fact. White holes are not science fiction. They are predicted by Einstein's own theory of general relativity. The equations that govern gravity, the very fabric of spacetime itself, allow for their existence. When we solve these equations for a simple, non-rotating black hole, described by the Schwarzschild metric, the solution famously includes both a black hole interior and a separate, disconnected region, a white hole interior. It is all part of the same mathematical map. For a more realistic, spinning black hole described by the Kerr metric, the geometry becomes even more exotic, suggesting pathways that could, in theory, connect to white hole regions. So why does this matter? It means the idea is not a wild guess. It is embedded in our most successful theory of gravity. However, physicists make a crucial distinction. A solution being mathematically valid does not mean it is physically possible in our universe. Most researchers label white holes as unphysical. The reason is a problem of birth. For a white hole to suddenly appear in the cosmos, it would have to begin its existence in an infinitely dense state, a singularity, and then explode. There is no known, natural process that could set up such a pristine, explosive beginning from the chaos of the universe. It would be like finding a movie that only plays in reverse, with no forward version ever having been recorded. So while the equations permit them, nature seems to have a profound aversion to creating them under normal conditions. Yet, this very theoretical possibility, this ghost in the machine of relativity, is what keeps the concept fiercely alive in physics. It is a tantalizing clue that our understanding of gravity, as perfect as it seems, might be incomplete, hinting that a deeper theory could reveal where these cosmic fountains might truly flow. That profound aversion nature seems to have for creating white holes points us toward a staggering possibility. If they are out there, they are not hiding in our galactic neighborhood. The most distant white holes would be relics from the dawn of time itself. In astronomy, distance is a direct window into the past. The light from a star 1 million light-years away has been traveling for 1 million years, so we see it as it was in that ancient past. To observe the most distant objects in the observable universe is to peer back to a time just a few 100 million years after the Big Bang, when the cosmos was a hot, dense, and violently energetic soup. It is within that primordial chaos that the rules of physics as we know them were stretched to their absolute limits. This is the only environment where theorists can plausibly imagine a white hole being born. The incredible pressures and temperatures of the universe's first moments could have forged these objects as cosmic fossils, frozen in time from an era when the very fabric of reality behaved differently. They would not be the end result of a dying star like a black hole, but a raw initial condition of the universe itself, a knot of space-time that began in an explosive state and has been erupting ever since. Picture a geyser in the cosmos, one that started spewing its energy 13.8 billion years ago, and whose light is only just reaching us now. Finding such an object would be like discovering a living dinosaur, a remnant of a law of physics that governed the infant universe but has since faded from view, leaving only these distant, brilliant echoes as evidence of a wilder, more explosive beginning to everything. The search for these cosmic fossils leads us to a thrilling possibility. One of the most compelling reasons to hunt for distant white holes is that they could explain some of the most powerful and mysterious explosions ever recorded. Imagine an event in deep space that unleashes in a mere millisecond more energy than our sun will emit in 80 years. Astronomers see these events called fast radio bursts, and they are utterly perplexing. Their source is a profound mystery. Now consider a white hole's defining behavior, a sudden, catastrophic eruption of all its stored matter and energy from a single point. The flash from such an event would be unimaginably bright, concentrated, and brief. It would not be the long, drawn-out fire of a supernova where a star collapses and then rebounds in a slower inferno. It would be more like a cosmic gunshot, a single, impossibly powerful spike of energy across the electromagnetic spectrum. The theoretical light curve, the graph of its brightness over time, would be starkly different. A supernova's curve rises and falls over weeks or months. A white hole explosion would spike almost instantly to an unbelievable peak and then vanish, as if a door in the universe slammed shut. This signature could match not only some fast radio bursts but also certain short gamma-ray bursts, the most luminous explosions since the Big Bang itself. We have catalogued these events for decades, always attributing them to colliding neutron stars or other extreme stellar deaths. But what if a fraction of them are not deaths at all? What if they are births, or more accurately, reverse deaths? The final explosive scream of a white hole that has been waiting since the beginning of time to disgorge its contents. Finding one would mean we have been misinterpreting the sky's most violent messages, hearing not a collision, but a cosmic fountain turning on for a single, brilliant moment before disappearing forever into the past. This violent cosmic gunshot creates a profound puzzle for the laws of physics. Our fifth fact confronts a fundamental rule of the universe. White holes appear to violate the second law of thermodynamics. This law states that entropy, the measure of disorder in a closed system, always increases over time. It is the reason a cup of hot coffee cools down, why a tidy room becomes messy, and why we remember the past but not the future. The universe is on a one-way journey from order to disorder. Now picture a white hole. It is a singularity that, from our perspective in time, suddenly and spontaneously erupts with an immense amount of highly structured matter and energy. It takes a state of ultimate density and disorder, the singularity, and transforms it into an expanding shell of planets, gas, and radiation. This looks for all the world like a massive, localized decrease in entropy. It is as if all the scattered pieces of a shattered vase suddenly flew up from the floor and reassembled themselves perfectly on the table. This is the core of the paradox. Einstein's beautiful equations of gravity allow for the white hole, but the relentless statistical law of thermodynamics seems to forbid it. It is a battle between the elegant symmetry of mathematics and the messy, one-way street of reality we all experience. For most physicists, this is the primary reason to doubt white holes can exist in our universe. They would be cosmic cheaters, creating pockets of impossible order in a cosmos forever sliding toward greater chaos. This violation is not a small detail. It strikes at the heart of our understanding of cause, effect, and the irreversible flow of time itself. If we ever found one, we would not just be discovering a new object, we would be witnessing a fundamental law of nature being broken, forcing a complete rewrite of the rules. The profound violation of thermodynamics forces us to ask where all that erupting energy could possibly go. This leads to a concept straight from science fiction, but grounded in the same mathematics. White holes are theorized to be the explosive exits of wormholes. The classic model, an Einstein-Rosen bridge, paints a stunning picture. On one side of the universe, a black hole's event horizon acts as a one-way entrance, a door that swallows anything that crosses it. Deep within the mathematical solution, this tunnel or bridge does not simply end at a singularity of infinite density. Instead, it theoretically connects to another region of spacetime where the geometry flips. That other end is a white hole, a one-way exit violently spewing out everything that fell into the black hole entrance. You would have a cosmic subway system with a black hole station here and a white hole station in a distant galaxy or even another universe entirely. The allure for interstellar travel is obvious, but the reality is brutally discouraging. The white hole exit is not a calm portal you step out of. Remember its defining nature. It is an erupting fountain of spacetime itself. Anything approaching it from within the wormhole would be met with an impassable wall of outward rushing energy and matter. It would be like trying to walk up the outflow pipe of a geyser at the moment it erupts. Furthermore, these theoretical bridges are catastrophically unstable. The moment even a single particle of matter tries to traverse the tunnel, the equations suggest the bridge would pinch off and collapse, severing the connection in a fraction of a second. So while the image is captivating, a glittering tunnel through the cosmos ending in a blinding flash of creation, it is ultimately a cosmic dead end. The white hole exit is less a welcoming doorway and more a theoretical exhaust pipe, firing the universe's waste heat and scrambled matter into some other corner of reality, a destination no traveler could ever survive. Even if a white hole existed, seeing its heart would be impossible. The observational challenge is a brutal paradox of its own nature. From within a white hole, light can escape, defying the gravitational prison of a black hole. But that theoretical clarity is instantly destroyed by reality. A white hole is not a serene, glowing orb. It is a continuous, catastrophic eruption. Matter and radiation will be blasting outward at velocities approaching the speed of light, creating a thick, turbulent, and utterly opaque shell of superheated plasma around the central singularity. It would be like trying to see the flame of a candle hidden inside the heart of a volcanic eruption. The light from the interior, carrying the secrets of its primordial origin, would be scattered and absorbed by the chaos of its own explosive output long before it could ever reach our telescopes. So astronomers are not hunting for a clear portal. They are searching for a specific, violent signature in the data. They would look for a point of light that appears from absolute nothingness in a region of empty space, brightening to an insane peak in milliseconds or seconds, and then fading just as quickly. It would be a cosmic flashbulb popping once and never flashing again. The spectrum of that fleeting light would be the real treasure. If it showed an abundance of primordial elements like hydrogen and helium, with almost none of the heavier elements forged in stars, it would be a smoking gun. That composition would point to a source that predates the first stars, a relic from the universe's raw infancy violently announcing itself. Catching such an event requires patience and next-generation eyes on the sky. Arrays of radio telescopes listening for the crackle of fast radio bursts, and space observatories with wide-field cameras scanning the deep, dark fields of the cosmos, must all work in unison, waiting for that one in a billion flash that does not fit any known stellar cataclysm. It is a search for a ghost in the light, a single, impossible note in the universe's chaotic symphony. Stephen Hawking gave black holes a deadline. His revolutionary theory of Hawking radiation proposed that these cosmic monsters are not eternal. Through bizarre quantum effects at the very edge of their event horizons, black holes can slowly leak particles, losing mass and energy over unimaginable timescales. For a stellar mass black hole, this evaporation would take longer than the current age of the universe, but the principle is devastating. It means black holes have a finite life, and their fate is not to sit forever, but to eventually fade away, shrinking to a point and winking out of existence. This quantum whisper complicates the white hole story profoundly. The classical mathematics of relativity, which paints that beautiful symmetrical picture of black holes connecting to white holes, does not account for this gradual decay. Hawking's work suggests the journey ends not with a bang, but with a whimper, a final, quiet pop of energy. Yet, the story does not end there. Some theoretical physicists working at the wild frontier where gravity meets quantum mechanics propose a startling alternative. They suggest that what we perceive as Hawking radiation is not the whole picture. As a black hole evaporates near its final moments, its internal quantum structure could undergo a radical transformation. Instead of vanishing, the remnant, now microscopic, could tunnel through the laws of physics into a new state, a white hole. In this view, the evaporation is not an end but a metamorphosis. The black hole's long, slow death throes are the prelude to a final, explosive rebirth on a quantum scale. This is the heart of a fierce debate. Classical relativity, with its timeless equations, allows for white holes as symmetrical twins. Quantum field theory, with Hawking radiation, suggests black holes simply evaporate. The true theory of quantum gravity, which we do not yet have, must reconcile these two wildly different endings. Is the fate of a black hole a silent fade to black, or is it a dramatic scene change, a cosmic plot twist where the villain's lair transforms into a fountain of new possibilities? The answer lies in the physics of the very, very small, where the fabric of spacetime itself may have something to say about its own ultimate destiny. That quantum metamorphosis points us toward the most promising frontier for white holes to become real. The key to their creation may not lie in the vastness of space, but in the bizarre, probabilistic realm of the very small. To understand how a white hole could be born, we must zoom in past atoms, past particles, to the fundamental fabric of reality. At this unimaginably tiny scale, the smooth, curved spacetime described by Einstein dissolves into a seething, chaotic froth. Gravity ceases to be a gentle curve and becomes a storm of fluctuating loops and knots, a quantum foam where the concepts of before and after lose all meaning. In this domain, the absolute power of a singularity is not the final word. Several cutting-edge theories of quantum gravity, like loop quantum gravity, propose a revolutionary alternative to the grim end of stellar collapse. They suggest that when a massive star exhausts its fuel and begins its fatal inward plunge, the crushing forces at its core do not lead to an infinitely dense point of no return. Instead, as the matter is squeezed beyond the Planck scale, the repulsive force of quantum gravity becomes overwhelmingly powerful. Imagine compressing a spring to its absolute limit, but instead of breaking, it hits a barrier of pure quantum pressure and rebounds. This is the concept of a quantum bounce. The collapsing star would reach a maximum density, a smallest possible volume dictated by the granular nature of spacetime itself, and then rebound, exploding outward. From our perspective in time, watching from outside, we would see a star collapse, but instead of forming a black hole's eternal event horizon, we would witness a brief, ultra-dense object that then violently erupts. This reborn object would have all the hallmarks of a white hole, a region of spacetime that cannot be entered, only exited, born from a quantum resurrection. It would be a cosmic phoenix forged not in fire but in the granular geometry of spacetime loops. This theoretical process elegantly sidesteps the thermodynamic paradox, as the bounce is not a reversal of time, but a physical rebound driven by the universe's smallest possible stitches. If true, it means white holes could be the universe's natural response to gravitational collapse, a secret second act written into the quantum code of reality, waiting to be observed in the distant echoes of a dying star's final, glorious rebound. The quantum bounce suggests a universe that resists true collapse, but this leads to a startling scale for its most ancient relics. The most distant white holes, those forged in the first instance of the Big Bang, might not be cosmic titans at all. They could be unimaginably tiny, existing at the smallest possible size the laws of physics allow, the Planck length. To grasp this scale, forget atoms. An atom compared to the Planck length is as vast as a galaxy compared to a single grain of sand. This is the realm where gravity and quantum mechanics collide, where our classical understanding of space and time shatters into a foamy, probabilistic chaos. In the searing heat of the universe's birth, fluctuations in this quantum foam could have been violent enough to pinch off microscopic regions of spacetime, creating Planck-sized knots of immense density. Some theories suggest these knots, these primordial white holes, would have been born erupting. Their entire life cycle, from explosive birth to final evaporation via their own version of Hawking radiation, could have lasted less than a trillionth of a second. They would have been cosmic firecrackers popping into and out of existence before the first particles had even properly formed. Yet another, even more fascinating idea proposes that some of these microscopic seeds did not instantly vanish. In the rapidly expanding fabric of the infant cosmos, they could have been stretched and inflated along with space itself. A white hole born at the Planck scale, 1.35 times 10 to the negative 35 meters across, could have been blown up to astronomical sizes by the relentless force of cosmic inflation. This means a white hole we might observe in the distant universe today, shining with the energy of 1,000 galaxies, could have started its existence smaller than any known particle. It is a breathtaking concept that the largest explosive objects we can conceive of may have quantum mechanical origins in the very smallest things possible. This connects directly to the most ambitious theories of quantum cosmology, which seek to describe the Big Bang itself not as a singular beginning, but as perhaps a quantum bounce from a previous universe or as a natural fluctuation in an eternal cosmic foam. Within that vision, white holes are not just mathematical curiosities. They are potential bridges between cosmic epochs, microscopic seeds of entire new regions of spacetime, erupting into existence and defining the large-scale structure of everything we see. Their faint, distant glow might be the dying light of the universe's quantum infancy. The universe constantly rains down bullets of pure energy. For over a century, we have known that Earth is under a ceaseless bombardment from outer space. These are cosmic rays, not rays of light, but atomic nuclei stripped of their electrons, accelerated to velocities so extreme they carry energies millions of times greater than anything our most powerful particle colliders can produce. They streak through the void and slam into our upper atmosphere, creating cascading showers of secondary particles. We detect them, but their origin is one of astronomy's longest-standing mysteries. The particles are charged, so their paths are bent and scrambled by the magnetic fields that crisscross our galaxy. By the time they reach us, it is impossible to trace a straight line back to their source. They are cosmic fingerprints with no clear suspect. Now consider the final, cataclysmic eruption of a distant white hole. In its final moments, as it disgorges all its remaining mass and energy, the environment around it would be one of unimaginable violence. Space-time itself would be convulsing, creating gravitational shocks and electromagnetic fields of staggering intensity. Any stray particle caught in that maelstrom would be whipped to near light speed, like a pebble in a cosmic tornado. A white hole would not just be a bright flash of light, it would be the ultimate particle accelerator, firing off atomic bullets with energies that dwarf even the most powerful supernovas. The key to linking them might lie in timing and composition. If a brief, inexplicable flash of gamma rays or radio waves from a distant point in the sky was followed, moments later, by a shower of ultra-high-energy cosmic rays with a specific primitive elemental makeup, it would be a compelling clue. We would have two separate messengers, light and matter, arriving from the same patch of sky, telling the same story of a sudden, catastrophic eruption. Finding that correlation would be like hearing a thunderclap and then feeling the raindrops hit, confirming a storm in a distant galaxy. It would turn these mysterious cosmic bullets from anonymous background noise into targeted evidence, each one a potential tracer round fired from the most powerful gun in the cosmos, a dying white hole announcing its final act across billions of light years. The universe's most powerful particle accelerators might be firing in the dark, but their deepest challenge is not to our instruments, it is to our minds. White holes do not just break the rules of thermodynamics, they shatter our most basic assumption about reality itself, that cause must always come before effect. This is the principle of causality, the unshakable foundation of all science and human experience. You drop a glass, it shatters. The cause, your hand letting go, precedes the effect, the broken pieces on the floor. Now try to apply that logic to a white hole born from the time-reversed mathematics of a black hole. From our perspective in the forward flow of time, a white hole simply appears. There is no collapsing star we can point to as its origin, no preceding cataclysm that creates it. The effect, a violent cosmic explosion, is the very first thing we observe. The cause, if it exists at all, lies in its future, in the moment something might fall into it which it can never allow. It is a cosmic event that seems to have no beginning, an answer without a question. This creates profound paradoxes. Imagine if you found a shattered wine glass on your kitchen floor, and as you stare at it, the pieces suddenly leap upward, reassembling perfectly in your hand. The effect, the broken glass, happened before the cause, you dropping it. A white hole presents the universe with the same dizzying puzzle, a splash in the cosmic pond that appears before the stone is thrown. How can physics make sense of such a thing? One radical resolution comes from the block universe model of time. In this view, championed by Einstein himself, past, present, and future all exist simultaneously in a static, four-dimensional block of spacetime. Our perception of a flowing now is an illusion of consciousness. In the block universe, a white hole is not a process that happens, it simply is. Its connection to a black hole is not a tunnel through time, but a fixed geometric structure like a mountain range connecting two valleys. The cause and effect are just labels we apply to different points on a timeless landscape. Another, even wilder, idea places white holes in a multiverse. Perhaps what we see as a spontaneous white hole explosion in our universe is the causal echo of a black hole collapse in a parallel, time-reversed universe. In that twin cosmos, our white hole is their black hole, and their cause becomes our effect, threading causality through a loophole in reality's fabric. These are not just thought experiments, they are necessary contortions of logic forced upon us by the mathematics. To accept a white hole is to stare into a mirror where time's arrow has flipped, where beginnings and endings trade places, and where the universe itself might be writing its history in reverse. This brings us to a crucial point of distinction. White holes are not the stuff of Saturday morning cartoons or sensational movie plots. They occupy a serious, if profoundly speculative, corner of theoretical physics. While you will not find them in an astronomy textbook yet, you will find them in the peer-reviewed papers of respected scientists pushing the boundaries of quantum gravity. Physicists like Carlo Rovelli, a leading figure in loop quantum gravity, have published detailed work exploring white holes as potential outcomes of stellar collapse or as remnants of the primordial universe. These are not flights of fancy, they are mathematical investigations into the extreme consequences of marrying Einstein's relativity with the quantum world. The equations are complex, the peer review is rigorous, and the debates are held in the halls of academic conferences. This work exists at the very frontier of human knowledge, a place where solid ground gives way to calculated speculation. It is the difference between a Hollywood scriptwriter imagining a wormhole and a cosmologist solving the Wheeler-DeWitt equation to see if one emerges from the math. The goal is not to prove they exist, but to ask a disciplined question: if our most fundamental theories are correct, what else might they allow? White holes represent one possible answer, a stress test for our understanding of reality. So when you hear about them, do not dismiss it as mere science fiction. See it instead as science in its most raw and ambitious form, a dedicated search for the hidden signatures of laws we have not yet fully written, conducted by thinkers who are willing to follow the math into the strangest of places, even if those places seem to defy every story we have ever told about the cosmos. The profound challenge to causality makes one thing perfectly clear: a confirmed detection of a white hole would revolutionize physics overnight. It would not be just another discovery, like finding a new exoplanet or a distant galaxy. It would be an earthquake that shatters the very bedrock of our understanding. Textbooks on gravity, thermodynamics, and cosmology would not receive a new chapter. They would be torn apart and rewritten from the first page. Our most cherished laws, the ones we teach as fundamental truths, would suddenly have a glaring, brilliant exception. The second law of thermodynamics, the unbreakable rule of increasing disorder, would be broken in plain sight. The classical picture of gravity painted by Einstein, beautiful and complete, would be shown to be a part of a larger, weirder story, and our models of the universe's birth and evolution would need to account for these violent, erupting relics from the dawn of time. The impact would cascade through every corner of theoretical physics. A single, unambiguous observation would act as the ultimate judge, validating or invalidating the leading contenders for a theory of quantum gravity. Did the detection show a Planck-sized remnant that might point toward loop quantum gravity? Did it exhibit a specific signature in its evaporation that could support a particular string theory model? For decades, these theories have been elegant mathematical constructions, debated in conferences but lacking a crucial experimental test. A white hole would be that test, a cosmic laboratory result delivered from 13 billion years in the past. The Nobel Prize would be the least of it. The discovery would crown a new era of human comprehension. But beyond the equations and the accolades, the true revolution would be in our cosmic perspective. We would have to accept that the universe is far stranger, far more creative, and far less bound by our intuitive arrows of time than we ever dared to believe. We would have proof that creation can erupt from nothingness, that endings can be beginnings, and that the cosmos holds secrets written in reverse. It would humble our science and expand our imagination in a single, blinding flash of light from the depths of space. The white hole's event horizon is the exact opposite of its dark twin. For a black hole, the event horizon is the ultimate point of no return, a one-way boundary in space you can cross inward but never escape. Cross that line and every possible future path leads inexorably toward the central singularity. A white hole's event horizon flips this rule completely. It is a one-way boundary you can only cross outward. From our perspective outside, it is an impenetrable barrier that actively repels the universe. Anything, even light itself, can stream out from within, but nothing, not a single photon or speck of dust, can ever fall in. Picture a cosmic fountain of unimaginable power, but instead of water, it is erupting space-time and matter. Now imagine trying to throw a pebble into the heart of that fountain. As the pebble approaches, it would encounter not a pull, but a push, a ferocious outward wind of energy and distorted space that grows infinitely stronger the closer it gets. The pebble would slow, stop, and then be hurled back outward as if it had hit an invisible, perfectly elastic wall. This is the white hole horizon in action, not a gravitational pit, but a gravitational hill of infinite steepness. From a distance, it might appear as a shimmering sphere of intense, scrambled light, a perfect celestial marble from which all of creation seems to be fleeing. Inside that barrier, every possible path for a particle points away forever. It is a prison of anti-gravity, a region of the cosmos that is violently, permanently, and absolutely off-limits to the rest of the universe, enforcing a solitary exile that lasts until the final moment of its explosive demise. That prison of anti-gravity, a region forever pushing the universe away, forces us to consider what could remain after its final flash. The most distant white holes might have died long ago, but their corpses could be all around us, woven into the fabric of the cosmos itself. This leads us to a breathtakingly speculative idea, one that connects these theoretical explosions to the universe's greatest mystery. Some cosmologists propose that stable, microscopic remnants of primordial white holes could make up a portion of dark matter. Think of dark matter as the universe's hidden skeleton, an invisible mass that holds galaxies together and shapes the cosmic web. We know it's there because of its gravitational pull, but for nearly a century we have had no idea what it actually is. All our searches for exotic particles have come up empty. So what if the answer isn't a new particle but a fossil? In the violent first moments of the Big Bang, countless quantum fluctuations could have birthed trillions upon trillions of microscopic white holes. Most would have evaporated instantly in a burst of Hawking radiation, but a special few, born with just the right mass, could have reached a state of perfect equilibrium. Their evaporation would slow to a crawl, granting them a lifespan longer than the age of the universe. These would not be erupting fountains, but cold, dark, and incredibly dense cinders, each one potentially weighing as much as a small asteroid, yet smaller than a single proton. They would be the ultimate dark objects, not emitting light, not reflecting it, and nearly impossible to absorb it. A swarm of such relics, drifting unseen through every galaxy, would exert exactly the kind of pure gravitational influence we attribute to dark matter. They would be invisible knots in the cosmic web, the ancient, silent ashes of the universe's first and most violent explosions. The challenge, of course, is proving it. How do you find something that does not interact with light, that is smaller than an atom, yet as massive as a mountain? It is a needle in a universe-sized haystack. But the mere possibility is a thrilling reminder that our greatest cosmic puzzles might be solved not by looking forward to new physics, but by looking back to the very first instance of creation, where the seeds of everything were sown in fire and quantum foam. The silent, dark remnants of ancient white holes pose a deep question about the universe's memory. But what if these objects hold the key to a modern physics crisis? For decades, a furious debate has raged around black holes, centered on a seemingly simple question: what happens to information? When a book is burned, the information, the words and ideas, is not truly destroyed. It is merely scrambled into heat and smoke. In principle, with a perfect understanding of physics, you could reverse the process, gather every particle of ash and wisp of gas, and reconstruct the book. Information in quantum mechanics is always preserved. This is a sacred law, yet a black hole seems to break it. Throw a book, a computer, or an entire star into a black hole. According to classical relativity, that information is lost forever behind the event horizon, eventually crushed into the featureless singularity. When the black hole evaporates via Hawking radiation, that radiation is purely thermal, random heat. No trace of the original book's information remains in the universe. This is the black hole information paradox, a fundamental conflict between quantum mechanics and general relativity that has stumped the greatest minds for 50 years. Now enter the white hole with a potential plot twist. If a black hole can, through a quantum bounce or a tunnel through space-time, transform into a white hole, then the information isn't lost at all. It is merely delayed. The white hole, in its final explosive eruption, could spew out all that scrambled information back into the cosmos. The book would be pulverized and its pages scattered across the galaxy, but the information, the quantum bits that made it unique, would ultimately be returned. It would be a cosmic recycling plant, not a shredder. This offers a tantalizing escape from the paradox, suggesting information is preserved through a dramatic two-act cosmic play, collapse followed by eruption. But the solution is far from clean. It introduces staggering new problems of timing and causality. From our perspective, the information falls into the black hole and vanishes for an incomprehensibly long time, potentially trillions of years, waiting inside the remnant until its white hole phase begins. During that eternity, the information is effectively gone from our universe, which still violates the quantum rule that information must never be truly inaccessible. Furthermore, when does the white hole decide to give it back? The process seems to require a coordination that defies our linear sense of cause and effect. The information return would appear utterly random and disconnected from the original act of falling in, like receiving a letter you mailed a trillion years after you wrote it from a return address that didn't exist when you sent it. So while white holes propose a dazzling resolution, they do so by deepening the mystery, trading one paradox for another that stretches the fabric of time itself to its breaking point. The information paradox reveals a universe struggling with its own rules, but white holes propose a more fundamental defiance of reality's architecture. Their gravitational signature would be unlike anything else in the cosmos. While a black hole's immense mass warps spacetime into a bottomless pit, a white hole would warp it into an impassable hill. This is not anti-gravity in the science fiction sense of a magical force field that cancels weight. It is a direct, brutal consequence of its reversed geometry in time. Picture the fabric of spacetime not as a still sheet but as a flowing river. A black hole is a whirlpool where the current drags everything inward toward the drain. A white hole is that same whirlpool, but with the film of reality running backward. The water erupts from the drain, pushing outward with tremendous force. Any object approaching it would not feel a pull, but a relentless push. The spacetime around it would be bulging outward, creating a slope so steep that nothing could climb up it to fall in. You would be standing at the base of a gravitational mountain that is actively growing taller, its slopes accelerating away from you. This repulsive effect is so complete that even light, struggling to move against this outward rushing spacetime, would appear to slow, redden, and fade as it fought its way toward the horizon, only to be swept back in the cosmic current. It is a region of the universe that is not just empty, but actively, violently exclusive, telling the rest of creation to stay away. That gravitational mountain, an impassable hill in space-time, points toward the most audacious idea of all. Our entire cosmic history might be the view from inside one. The Big Bang itself has been described as a primordial white hole. Think about the defining characteristics. A white hole is a singular point from which all matter and energy violently erupts, a region of space-time that cannot be entered from the outside. Now describe the Big Bang. It is the singular event from which all matter and energy in our universe emerged, a point of infinite density from which space-time itself expanded. Nothing could have entered that initial state from our universe because our universe did not yet exist. The parallels are too striking to ignore. Some cosmologists, like the physicist Raj Pathria, have explored this mind-bending possibility in detail. What if the Big Bang was not a unique, absolute beginning, but simply the white hole eruption from another parent universe? In this staggering model, our entire cosmos, with all its galaxies, stars, and planets, is not the whole story. It is the interior of a white hole that formed in a larger, pre-existing meta-universe. We are not looking out at the cosmos from a special place. We are living within the aftermath of a single, spectacular explosion in a grander reality. The event horizon of that parent white hole would not be a sphere in our sky, it would be our past. It is the ultimate cosmic horizon, the moment of creation itself, forever receding from us as space expands. We can never cross back through it, just as nothing can cross into a white hole. We are forever flowing away from that initial eruption, riding the aftermath of the universe's birth. The visuals this conjures are profound. Picture not a white hole as a distant object in space, but as the very fabric of your reality. The blinding flash of the Big Bang is the white hole's singularity disgorging its contents. The subsequent expansion and cooling of the universe, the formation of the first elements, the ignition of stars, all of it is just the detailed interior structure of that one unfathomably large explosion. In this view, every galaxy is a ripple in the erupting fire, every planet a cooled ember from that initial cosmic forge. It transforms our origin story from a lonely, inexplicable beginning into a potentially natural process in a richer, multi-layered reality. If true, it means we are not just studying white holes, we might be living inside the grandest one of all, a thought that turns the entire universe into a single, breathtaking clue. The grandest white hole of all might be our own universe, but the smallest ones could be born in the emptiness between your fingertips. The void of space is not truly empty. According to quantum field theory, it is a seething, bubbling sea of potential. At the tiniest scales, pairs of virtual particles and antiparticles constantly wink into existence, borrowing energy from the vacuum for a fleeting moment before annihilating each other and vanishing. This is the quantum foam, the fundamental fizz at the foundation of reality. Now, place this quantum chaos at the edge of a black hole's event horizon, or within the crushing density of the early universe. Under such extreme gravitational stress, the rules can bend in spectacular ways. Instead of a simple particle pair, the fluctuation could, in theory, pinch off a microscopic region of spacetime itself, creating a self-contained tunnel. One end of this tunnel would behave like a tiny black hole, the other like a tiny white hole. This is a theoretical baby white hole, a quantum wormhole born from the vacuum's own restlessness. It would be a fleeting spark of reversed gravity, erupting with its borrowed energy before the debt is called in. Its entire life cycle, from birth to explosive evaporation, could be shorter than a trillionth of a second, a blink so fast it makes an atomic clock seem frozen in time. The instability is total. The moment it forms, the intense outward pressure from its white hole end and the relentless pull from its black hole end would tear the fragile structure apart, collapsing it back into the featureless vacuum foam. It would be less like a star and more like a bubble in a boiling pot, forming and popping before you could even register its shape. This is why we might never directly detect one. Our instruments are built to catch signals that persist, even for nanoseconds. A baby white hole's signature would be a burst of energy so unimaginably brief and confined to such a minuscule volume that it would be lost in the constant background hum of the quantum world. It would be like trying to hear a single raindrop hit the ground during a hurricane, yet their theoretical existence is a crucial piece of the puzzle. They represent the ultimate marriage of quantum mechanics and gravity, suggesting that the fabric of spacetime itself might be dynamic and creative at its core, capable of sprouting these bizarre structures as naturally as the ocean sprouts waves. If spacetime can spontaneously generate these ephemeral fountains, even for an instant, it hints that the laws of physics do not forbid white holes outright. They merely confine them to realms of scale and time that are, for now, just beyond the edge of our perception. A visible singularity would tear the curtain of reality clean off. This brings us to a principle so fundamental, it is known as cosmic censorship. Proposed by the physicist Roger Penrose, this is not a law, but a profound hope about how the universe maintains order. The hypothesis suggests that nature abhors a naked singularity. It insists that every singularity, every point of infinite density where the laws of physics break down, must be hidden from view, forever veiled behind the protective curtain of an event horizon. A black hole perfectly obeys this rule. Its terrifying singularity is locked away, causally disconnected from the rest of the universe, unable to wreak havoc on the predictable fabric of spacetime outside. Now place a white hole in this picture. Its defining nature is to erupt, to be an exit only. If it truly exists as a classical object, its singularity would not be hidden behind an event horizon you can fall into. It would be exposed, it would be naked. Picture not a black sphere, but a blinding, dimensionless point of light, a cosmic sore thumb where gravity becomes infinite and the smooth equations of Einstein dissolve into screaming nonsense. At that point, cause and effect would cease to have meaning. Predictability, the very foundation of science, would vanish. You could theoretically observe events that have no cause or send signals into your own past, creating paradoxes that unravel the logical sequence of reality. A naked singularity is not just a weird object, it is a hole in the rational universe. White holes, by their very theoretical design, challenge cosmic censorship head-on. They are the ultimate test case. If we ever found one, it would prove that Penrose's hopeful hypothesis is wrong, that the universe is not so tidy. It would mean the most violent breakdown of physics is not locked away in prison cells, but can sometimes stand in the open, a glaring exception to the cosmos's otherwise orderly rules. This is why white holes are not merely astronomical curiosities, they are philosophical grenades. Their search is a direct assault on our understanding of whether the universe plays by consistent, predictable rules everywhere, or if it allows for lawless zones where anything, absolutely anything, can happen. That philosophical grenade, the threat of a naked singularity, demands a deeper symmetry. Perhaps the universe avoids such chaos by linking these violent opposites into a single, balanced whole. In some of the most elegant unified theories of physics, white holes and black holes are not separate monsters at all. They are two faces of the same cosmic entity, two sides of the same coin. This idea finds beautiful expression in theories like Einstein-Cartan theory, an extension of general relativity that incorporates the intrinsic spin of particles. Here, the intense gravitational collapse of a spinning star does not end in a dead end. Instead, the mathematics naturally guides the collapsing matter through a bridge, an Einstein-Rosen wormhole, and out the other side as an erupting white hole. But here is the breathtaking twist: that other side might not be in our universe. The white hole exit could exist in a parallel universe or in a different region of our own cosmos, so distant it appears disconnected. In this view, every black hole birth is simultaneously a white hole birth somewhere else. They are eternally linked, forming a single structure, a gravitational circuit. Picture the cosmos not as a collection of isolated pits and fountains, but as a vast network of tunnels with matter flowing in one end and erupting from the other, maintaining a perfect hidden balance. The visual is stunning. A rotating black hole connected to its white hole twin would trace out a shape like a cosmic infinity symbol in spacetime, a loop of gravity where entrance and exit are forever joined. This provides a profound elegance to the universe. It suggests that for every act of destruction, there is a corresponding act of creation elsewhere. The terrifying singularity is never truly naked because it is always the throat of a bridge, the turning point in a grander circuit. The information that falls into the black hole is not lost, it is simply transferred, emerging scrambled but intact from the white hole in another realm. This cosmic duality resolves paradoxes with breathtaking grace, painting a picture of a universe that is fundamentally connected, balanced, and whole, where even the most extreme phenomena are part of a continuous, beautiful loop. This cosmic infinity loop of matter and energy would announce its presence with a distinct color in the sky. The light fleeing a white hole carries a unique fingerprint, one dictated by its warped relationship with gravity. As a photon escapes the fierce outward rush of spacetime near the horizon, it must climb a gravitational mountain, but unlike a climber who loses energy, light gains it. The immense gravitational well bestows extra energy upon the escaping photon, compressing its wavelength. This shifts its color toward the blue end of the spectrum, an effect physicists call gravitational blue shift. It is the exact opposite of the farewell we see from a black hole. Light struggling to escape a black hole's pull loses energy, stretching into longer, redder wavelengths, a gravitational redshift that is a hallmark of these dark giants. For a white hole, the story flips. Its repulsive gravity acts like a cosmic slingshot, imparting energy to anything leaving it. Imagine a siren on a police car rushing toward you. The sound waves compress, raising the pitch. Now picture that siren is light, and the rushing motion is the explosive expansion of spacetime itself, boosting the light's energy and tinting it blue. This creates a potential detection clue of extraordinary power. Astronomers would search the brief, brilliant flash of a candidate explosion, not just for its intensity, but for the specific color of its light. If the spectrum reveals a powerful, uniform blue shift that cannot be explained by the object's motion through space alone, it would be a tantalizing signal. It would suggest the light did not merely travel through the cosmos, but fought its way out of a ferocious, repulsive gravity well, gaining a blue tint on its journey to our telescopes. That specific hue, imprinted on the light from a sudden, inexplicable eruption, could be the signature we need to separate a white hole's death cry from all other cosmic catastrophes. Blue light from a cosmic geyser might be our best clue, but the universe seems determined to snuff such fountains out before they can even begin. A white hole is not just improbable, it is theoretically unstable on a fundamental level. Imagine building a castle on a foundation of repelling magnets, where the very stones you use want to push each other apart. That is the precarious existence of a white hole. The mathematics reveal a fatal flaw. It's defining one-way eggs. It is also its greatest vulnerability. The moment any external matter or energy, even a single stray photon of light, attempts to cross its repulsive horizon, the delicate balance shatters. That incoming particle does not simply bounce off. Its presence introduces a tiny amount of mass energy to the system. In the bizarre geometry of general relativity, that is enough to tip the scales. The equations show that this interaction would trigger an irreversible process, either causing the white hole horizon to violently collapse in on itself, transforming the entire object into a black hole, or causing the eruptive throat to pinch shut entirely, sealing the white hole off from our universe forever. It is a cosmic catch-22. To be a white hole, it must repel all external influence, but the universe is not empty. It is filled with dust, gas, radiation, and the faint glow of the cosmic microwave background. There is no perfect vacuum. Therefore, a classical white hole trying to exist in our cosmos would be under constant bombardment, a sitting duck in a shooting gallery of particles. Its lifetime would be fleeting, potentially shorter than the blink of an eye on cosmic timescales. This theoretical instability makes the very idea of a distant, ancient white hole seem not just unlikely, but almost miraculous. For one to have survived from the primordial universe to the present day, it would have needed to form in a region of absolute, pristine emptiness, a perfect void that has remained untouched by a single atom or photon for over 13 billion years. Or it would require a mechanism that actively sustains its explosive state against this inevitable collapse. This is why many physicists look toward the quantum realm for answers. Perhaps a white hole is not a static object, but a dynamic quantum process, flickering in and out of existence so quickly that it evades the fatal interaction, or rebounding continuously in a cycle of collapse and eruption at the smallest scales. The distant white holes we dream of detecting, then, would not be serene beacons. They would be the rarest of cosmic accidents, violent flickers in the dark that somehow defied the universe's relentless push toward equilibrium, surviving just long enough for their dying light to cross the vast gulf of space and time to reach our eyes. The data proving these cosmic phoenixes might already exist, hidden within the light of the infant universe. Our hunt has moved from pure theory to the meticulous analysis of photons collected by the most powerful eyes ever built. The James Webb Space Telescope is not just looking at distant galaxies, it is staring directly into the era where primordial white holes could have formed and died. Every speck of light in its breathtaking deep-field images has traveled for over 13 billion years, carrying stories from a time when the cosmos was a mere fraction of its current age. Astronomers are now scouring these datasets for anomalies, for single points of light that appear, blaze with impossible brilliance, and then vanish without the lingering afterglow of a supernova or the telltale signature of a merging star. They are searching for the ghost in the machine, a flash that matches no known template. Simultaneously, vast arrays of radio dishes, like the square-kilometer array pathfinders, listen to the static of the cosmos, their digital ears tuned to catch the millisecond crackle of a fast radio burst whose location and energy defy explanation. The search has become a forensic exercise in big data. Scientists are training machine learning algorithms to sift through petabytes of observational archives, looking for the 1 in a billion outlier that could be the signature of a white hole's final defiant eruption. This means the evidence might not be found in a new observation tomorrow, but in a forgotten dataset from a decade ago, a strange blip that was once dismissed as instrument error or cosmic noise. The next great discovery in astrophysics could come from a graduate student running a new analysis on old numbers, connecting dots across wavelengths and time to reveal a pattern that was always there, waiting for us to understand what we were seeing. The universe has likely already sent us its message, a single, brilliant postcard from the edge of time. It is now our task to decipher the handwriting. Our journey through 25 facts has been a wild ride across the fabric of reality itself. We have chased the ghostly echoes of time-reversed black holes, stood at the precipice of quantum bounces where collapsing stars might rebound into fountains of creation, and witnessed the theoretical flash of cosmic explosions that could rewrite the laws of physics. We have seen how these objects challenge our deepest assumptions about cause and effect, order and chaos, and the very arrow of time. White holes are not confirmed destinations on our cosmic map, but they are the most thrilling signposts we have, pointing toward the vast, uncharted frontier where human imagination and pure mathematics collide. They represent the ultimate question mark, a challenge to keep looking deeper, thinking stranger, and daring to believe the universe is more wonderfully bizarre than we have yet proven. So now we pass the question to you. Of these 25 mind-bending facts, which one completely reshaped your view of the cosmos? Was it the idea that our entire universe could be inside a white hole, or the possibility that dark matter is made of their ancient, silent ashes? Let us know in the comments below. If you crave more deep dives into the universe's greatest mysteries, be sure to subscribe. As you look up at the night sky tonight, remember that every point of light, every dark void between the stars holds secrets waiting to be unraveled. The cosmos is not a static painting, it is a story still being written, and we are just beginning to read the first few astonishing pages.